Hello students, welcome to the course CS371 Data Communication and Networks. I am Dr. Munir Omar. Today we will resume the topic flow control and error control. We have studied about this topic in the previous lecture and it was about the noiseless channel. Today we have noisy channel for the flow control and error control. So these are the contents for our today's lecture. First, we will look into the noisy channel. Then we have three protocols used for the noisy channel. The first one is stop and wait ARQ protocol. ARQ stands for automatic repeat request or automatic repeat query. This one is somehow similar to the previously studied protocol, which was stop and wait for the noiseless channel. After that, we will study about the go back and ARQ protocol, and this one is a bit different. Here we will have multiple frames transmitted from the sender side, and for multiple frames we will have fewer, or we can say that for multiple frames there would be one acknowledgement, and in case of stop and wait, for each frame transmitted there was one acknowledgement. Then we have a better version, that is selective repeat ARQ. It is an advanced version of go back protocol, and there are some flaws in the go back and protocol, so those flaws are covered by the selective repeat ARQ protocol. So we have studied the simplest protocol and stop and wait for noiseless channel in the previous lecture. Now we are moving towards the noisy channel, and in noisy channel we have three protocols: stop and wait ARQ, go back N ARQ, and selective repeat. So we will study all these protocols in this lecture. So we have got the idea of stop and wait protocol that was used in the noiseless channel in our previous lecture. Now we will use similar procedures in the noisy channels too, and in noisy channels we have three protocols, and we will discuss these three protocols in this lecture. Error correction in stop and wait ARQ is done by keeping a copy of the send frame and retransmitting of the frame when the timer expires. In stop and wait ARQ, we use the sequence numbers to number the frames. The sequence numbers are based on modulo 2 arithmetic. Here we have the design of stop and wait ARQ protocol, which is the first protocol used for noisy channel. The sending device keeps a copy of the last frame transmitted until it receives an acknowledgement from the receiver. This acknowledgement shows the status of delivery of the frame. A data frame uses a sequence number. An acknowledgement frame uses an acknowledgement number. Here we have sequence number with data frame, and here we have acknowledgement number in the acknowledgement frame. Also, there is one another thing, that is the control variable, which identifies that which frame should be transmitted. So all the frames are numbered, and according to these numbers the order of frames are decided. In fact, the sequence numbers for the next frame to be sent are either 0 or 1. On the other side, the receiver has a control variable which we call R, receiver next frame expected, which holds the number of the next frame expected. When a frame is sent, the value of Sn is incremented modulo 2, which means if it is 0, it becomes 1 and vice versa. When a frame is received, the value of R is incremented by modulo 2, which means if it is 0, it becomes 1 and vice versa. The events can happen at the sender side. One event can happen at the receiver side. Variable Sn points to the slot that matches the sequence number of the frame that has been sent but not acknowledged, while R points to the slots that matches the sequence number of the expected frame. The data link layer takes packets or data from the network layer and then passes data towards the physical layer. Also, these packets are converted into frames at the data link layer. Meanwhile, the data link layer also receives some frames from the physical layer regarding the transmitted frames. On data link layer, there is an algorithm which is always in execution, or we can say that the statements inside the algorithm are repeated forever. This algorithm takes data or request from the network layer as well as the notification from physical layer. The requests are made for packet delivery and notification are made for the acknowledgements. And also there is a timeout event which shows the duration. If a notification is not received in a particular period of time, then it is assumed that the data is not transmitted, or the data transmitted got corrupted or not received at the receiver. At receiving end, a similar algorithm is used at the data link layer, and this algorithm takes notification from the physical layer. These notifications identify the reception of frames from the medium. This is the algorithm for stop and wait ARQ at the sender side. We first notice the presence of S, the sequence number of the next frame to be sent. This variable is initialized once in the beginning beyond this line number 6, and then it is incremented every time a frame is sent, which is here at line number 13. So in the beginning, the algorithm checks whether there is any request to send data which is generated by the network layer, and also the value of a variable which is can send is checked. If you remember, we have already studied this variable in our previous lecture. So if these two values are true, then the first thing is to get data from the network layer, then make a frame according to the sequence number, store that frame as per the sequence number, and send that frame, and also start the timer. After that, increase the value of sequence number and make the can send as false. And then at line 16, wait for event. This event can be either timeout or notification. It can be a request from network layer, but the most important is timeout and notification. These are considered with this can send and the request to send from the network layer. After that, the next F statement is about the acknowledgement arrival. So if the arrival notification event is occurred, then receive the acknowledgement frame, and if it is not corrupted and the acknowledgement number equals the sequence number, then stop the timer. So if the acknowledgement number is according to the sequence number and the received acknowledgement is also not corrupted, then it means that everything is going well. So after that, we don't need the copy of frame which we stored before the transmission. So we must delete that copy. So we purge that frame as we don't need the copy of that frame, and after that we make the value of can send as true. This block is about the input from the physical layer, which is the notification from physical layer. Then for this timeout, we have another block which is here. If event timeout, if the time expires, then start timer and reset the value of sequence number or decrement. Actually, we incremented this sequence number, so we must decrement it again and retransmit this frame again. This algorithm is used at the receiver side. It is somehow similar to the noiseless channel, but there are some major differences. First, all arrived frames that are corrupted are ignored. So after the reception of frame, if a frame is corrupted, then go to sleep mode, means there is no need of acknowledgement. The time would expire and the sender would retransmit the same frame again. If the sequence number of the frame is the one that is expected, the frame is accepted and the data are delivered to the network layer. And also the value of R is incremented. However, there is one point here. Even if the sequence number of data frame does not match the next expected frame, an acknowledgement is sent to the sender. This acknowledgement, however, just reconfirms the previous acknowledgement instead of confirming the frame received. This is done because the receiver assumes that the previous acknowledgement might have been lost. The receiver is sending a duplicate frame. The recent acknowledgement may solve the problem before the timeout does. This diagram can be used for wait and stop ARQ algorithm. Here, the sender takes a frame according to the SN. So suppose it is taking the first frame, that is frame 0, and it transmits this frame towards the receiver. At the same time, it also starts the timer. The receiver, when receives this frame, checks it, and if the data is not corrupted, then according to this R, the acknowledgement is transmitted towards the sender. Upon reception of acknowledgement, the sender transmits the frame number 1, which is the second frame, and also restarts the timer. Meanwhile, this frame number 1 is not transmitted due to some reason, and the sender is not aware whether it is transmitted or not, and it waits until the timeout. After the timeout, the sender assumes that this frame number 1 is not transmitted to the receiver as it has not received any sort of acknowledgement from the receiver. So it resends the frame number 1 towards the receiver. Upon reception of frame number 1, the receiver sends another acknowledgement to the sender. Now here one acknowledgement is lost, and again the sender is not getting any sort of acknowledgement, so it must resend the frame again as the time is out. Now we are moving towards the go back and automatic repeat request algorithm for noisy channel. In the go back n protocol, the sequence number are modulo 2 power m, where m is the size of the sequence number field in bits. To improve the efficiency of transmission, multiple frames must be in transition while waiting for acknowledgement. Simply, we can say that we will have multiple transmission, and for those multiple transmission we will have a single acknowledgement from the receiver. Note one thing: while transmitting these multiple frames, the copies of all the frames are kept. In case we don't get the sender don't get any acknowledgement, then all those frames are retransmitted. Frames from a sending station are numbered sequentially. Because we need to include the sequence number of each frame in the header, we need to set a limit. If the header allows m bits for sequence number, then the sequence numbers range from 0 to 2 power m. For example, if m is 4, the only numbers are 0 through 15 inclusive, that is 2 power 4. However, we can repeat the sequence. So the sequence numbers are from 0, 1, 2, 3, and so on, depending on the size of M. In this protocol, we use the concept of sliding window that defines the range of sequence numbers that is in the concern of the sender and receiver. Simply, we can say that the sender and receiver need to deal with only part of possible sequence numbers. Like here, we have this range, so sender and receiver are dealing with this range. The send window is an imaginary box covering the sequence numbers of data frame which can be in transit. In each window position, some of these sequence number define the frames that have been sent, and other define those that can be sent. These can be sent. As we know that the maximum size of the window would be 2 power m, or 2 power m minus 1. So here the size of m is 4, so it is giving us values from 0 to 15, and in this window we are having two parts. The first part is about the frames sent but these are not acknowledged, and the second part is about the frames which are to be sent but depending on the acknowledgement of these frames. Once we get acknowledgement for these frames, after that these frames, the remaining frames, would be sent. So here we have a range of frames which are sent, but the status of these frames is unknown. Means that we have not received any sort of acknowledgement from the receiver. Three variables define its size and location anytime. We call these variables as SF, the send window, or the first outstanding frame, then SN, the sent window, the next frame to be sent, and S size, the send window size. The variable SF defines the sequence number of the first or the oldest outstanding frame. The variable Sn defines the sequence number that will be assigned to the next frame to be sent. And this S size is used to identify the size of the window, which is fixed in this protocol. So here these frames are already acknowledged, and after getting the acknowledgement of these frames, the sender sent these frames, and these frames need to be acknowledged by the receiver. If the sender gets acknowledgement about these frames, then it would send the rest of the frames starting from the SN. So the send window is an abstract concept defining an imaginary box of 2 power m minus 1 with three variables SF, SN, and S size. The send window can slide one or more slots when a valid acknowledgement arrives. In previous case, for each transmitted or sent frame, there was one acknowledgement. And here, one acknowledgement can be used for more than one frames. This entire procedure is from the sender, or we can say it is about the send window. Then we have the receive window, which is at the receiving side. The receive window makes sure that the correct data frames are received and that the correct acknowledgement are sent. The size of the receive window is always 1. The receiver is always looking for the arrival of a specific frame. Any frame arriving out of order is discarded and needs to be resent. So here in this figure, we are having the receive window, and we are getting a frame from the sender, and before this frame these frames are already acknowledged, and these frames are expected to be received. Once the window slides, after that these frames would be transmitted by the sender. Note that only one variable Rn, that is for receive window, or next expected frame, to define this abstraction. The sequence number to the left of the window belongs to the frames already received and acknowledged, and the sequence number to the right of this value defines the frames that cannot be received until this one is processed or this one is acknowledged. The receive window is an abstract concept defining an imaginary box of size 1 with one single variable Rn. The window slides when a correct frame has arrived. Sliding occurs one slot at a time. This figure shows the design of this protocol. We can see that multiple frames can be in transit in the forward direction from sender to receiver. And from receiver, we have multiple acknowledgements in the reverse direction. The idea is somehow similar to the previous protocol, but here note one thing, that we are sending multiple frames with respect to fewer acknowledgements. The frames to be sent start from SF to SN. and all these are sent in a block or one by one, and for all these we get only one acknowledgement from the receiver. In this figure we can compare the window size of 3 against a window size of 4. If the size of window is 3, that is less than 2 power 2, and all three acknowledgements are lost, the frame timer expires and all these three frames are resent. On the other hand, if the size of window is 4, that is equal to 2 power 2, all the acknowledgements are lost and the sender will resend a duplicate of frame 0 here. However, this time the window of the receiver expects to receive frame 0, so it accepts frame 0 not as a duplicate but as the first frame in the next cycle, so there is no error. Remember that we have sizes of window, so it is 2 power 2, that is equal to 4, so it would start from 0 to 3, and after the transmission of these frames again it would start from 0. So we can say that in the go back n ARQ, the size of send window must be less than 2 power m. In previous example it was 2 power 2. The size of the receiver window is always 1, as we have seen this in our previous slides. This is the algorithm for go back n at sender side. First, we initialize three variables, as we know that there are three variables used at the sender side. So we have SW, this is actually the size, this is the start, and this one is the end. Unlike the stop and wait ARQ, this protocol allows several requests from the network layer without the need for other event to occur. So we just need to be sure that the window is not full, which is at line 10. If the window is full, the request is just ignored and the network layer needs to try again. So according to this algorithm, first we initialize three variables, then we have an infinite loop. After that, we wait for the event, which would be from the upper layer or the lower layer or the timer. And if it is a request to send, then check if the window is full or not. If it is full, then go to sleep mode. The network layer would attempt again for sending its data towards the data link layer. And if it is not full, if the window is not full, then the data would be accepted or gathered from the network layer. The frame would be made, it would be stored, and after that it would be transmitted. And also the value of Sn would be increased by 1. And if the timer is not running, then start timer, because we need timer in these algorithms, both the previous one and this one. So we must start the timer every time in this if statement. After the reception of acknowledgement frame, we first receive the acknowledgement and then check whether it is corrupted or not. In case the acknowledgement is corrupted, then the sender goes to the sleep mode, and if the acknowledgement is valid, means that acknowledgement number is greater than SF and less than or equal to SN, then the stored frames are deleted, because there is no need to keep such frames, as these are already transmitted successfully, and the value of SF is also incremented. Once the operation is performed, once the frames are transmitted successfully, after that the timer is also stopped. And for timeout, we have also an if statement. If we get an event for timeout, or we can say if the time expires, then we restart the timer and put the value of sf into a temporary variable and initiate a while loop. Actually, this loop is used to retransmit the frame to sf, and after that the value of sf is also incremented. Now this is the algorithm for go back n at the receiving site. In the beginning, Rn is initialized. After that, we use a while loop for infinite repetition of all these statements. So the receiver must wait for an event. Actually, this event would be the reception from the physical layer. Upon the arrival notification, or we can say if the data link layer at receiving end receives data notification, so it must receive the frame. After that, it must check whether this frame is corrupted or not. Here, note one thing: in the checking, it is also checked that whether the frame is in correct order or not. If it is not in correct order, then it would be considered as corrupted. So if the frame is corrupted, then the receiver would move to the sleep mode, as there is no need to send any sort of acknowledgement because the frame is already corrupted. So the sender would retransmit the frame upon the expiry of time. If the sequence number is equal to the Rn, which is the expected frame, and definitely it would not be corrupted, so the frame is delivered to the network layer or moved upward to the network layer, and after that the next frame is adjusted by changing the value of Rn or by incrementing it by 1, and after that an acknowledgement is sent back to the sender according to this Rn frame. So this block repeats forever. Next time the value of Rn would not be 0, it would be another frame. The go back n ARQ simplifies the process at the receiver side. The receiver keeps track of only one variable, and there is no need to buffer out of order frames. They are simply discarded. If any frame is out of order, then some received frame along that out of order frame would be discarded. However, this protocol is very inefficient for a noisy link. In a noisy link, a frame has a higher probability of damage, which means the resending of multiple frames may get more bandwidth. As we know that for multiple frames, we have fewer acknowledgements, or for more than one frames, there would be one acknowledgement, and if one frame among many frames is corrupted, then all those frames would be retransmitted, and this would consume higher bandwidth, and this is an inefficiency in the transmission. For noisy links, there is another mechanism that does not resend n number of frames or multiple frames. We just send a particular frame which is damaged, and that mechanism is called Selective Repeat Arq. So we are moving towards the selective repeat ARQ, which is the last protocol in this topic. And this protocol is much better than go back and ARQ for noisy channels. In the selective repeat ARQ, we use two windows, a send window and a receive window. But there would be difference between the windows in this protocol and the ones in go back, and the size of send window would be smaller. This figure is for the selective repeat ARQ at sender side. Here the size of window is a bit smaller than previous protocol. Its size is 2 power m minus 1. Previously it was 2 power m. So suppose we have 4 bits. So in previous example, in previous protocol, it was 2 power 4, that was 16 from 0 to 15. But here it would be less than 15, it would be 8 as per the formula. The smaller window size means less efficiency in filling the pipe, but the fact that there are fewer duplicate frame can compensate for this. The protocol uses the same variables as we discussed in the go back n, which was the previous protocol. So here we have SF, SN. These are same as we saw in the previous protocol. Same situation here. Frames already acknowledged beyond this SF, and beyond SN frames that are to be sent. Actually these frames are ready and these would be transmitted once the sender get the acknowledgement for these frames. And beyond this value, the S size, these frames are not ready and these cannot be sent. And this figure shows the selective repeat ARQ for receiving side. This one is also different from the previous protocol. It is actually similar to the selective repeat ARQ at the sender side. First, the size of receive window is the same as the size of send window, and the selective repeat protocol allows as many frames as the size of the receive window to arrive out of order and be kept until there is a set of order frames to be delivered to the network layer. In previous protocol, we considered the sender considered the order of frames, but here the order of frames is not considered. We can say that all the frames in the send frame can arrive out of order and be stored until they can be delivered. Here these frames are received and these are waiting for their neighbors to arrive. Once all these frames are received, then these would be delivered to the network layer. The design of selective repeat ARQ is similar to the design of previous protocol. Here we have one another thing, that is negative acknowledgement. And most of the things are somehow similar in the design. This figure compares the window size of 2 with the window size of 3. If the window size is 2 and all the acknowledgements are lost, the timer for frame 0 expires and frame 0 is resent. Here all the acknowledgements are lost, so frame 0 is retransmitted. However, the window of receiver is expecting frame number 2 after this frame number 1, so the duplicated frame would be discarded correctly. Here when we have the frame size equal to 3, and we say that all the acknowledgements are discarded, or we can say these are lost, the sender sends a duplicate of frame number 0. At this time, the window of the receiver expects to receive frame 0, as 0 is the start of window as per 2 power n minus 1. So it accepts frame 0 not as a duplicate but as the first frame in the next cycle. So this is clearly an error. This is the algorithm for sender side selective repeat algorithm. The heading of the request event is similar to that of previous protocol, except that one timer is started for each frame sent. The arrival event is more complicated. Here in the arrival, we may get acknowledgement or negative acknowledgement, ACK or NAK. If a valid NAK frame arrives, we just resend the corresponding frame. If a valid ACK arrives, we use a loop to purge the buffers, stop the corresponding timer, and increase the value of SF, or move the left wall of the window. The timeout event is simpler here, only the frame which times out is resent. And in case of timeout, it's quite simpler. Here, the selected frame is sent only in case of timeout for a particular frame. So that particular frame would be sent. This is the algorithm for selective repeat at receiver side. Here we need more initialization. Previously we initialized only the value of Rn, and now we need some additional values to be initialized. In order not to overwhelm the other side with NAK, negative acknowledgement, we use a variable NAK sent. To know when we need to send an acknowledgement, we use ACK needed. Both these are initialized as false in the beginning. We also need a set of variables to mark the slots in the receiving window once the corresponding frame has arrived and is stored. If we receive a corrupted frame and a NAK has not yet been set, we mark NAK sent as true, and also before doing this we send NAK to the other side that we have not received the frame we expected. If the frame is not corrupted and the sequence number in the window is present, we store the frame and mark the sequence number as true. If contiguous frames starting with Rn have been marked, we deliver their data to the network layer and slide the window. Also purge the Rn value. At the end, we also set the value of acknowledgement needed and assign false to ACK needed and NAK sent as false. So in today's lecture, we studied about the noisy channel, then the three protocols, which are stop and wait ARQ, go back and ARQ, and selective repeat ARQ. We also studied about the algorithms used in these protocols, having some sample values, and checked their figures or designs. If you have any question, you can put your comments in the KCMS. Allah Hafiz.